Ladies and gentlemen, welcome back to Supercomputing Asia 2022. We are pleased to start off with 4 presentations right here. And now, for those of you on the online world, thank you for tuning in good time as well. Now, we have the first presentation, and this is going to be by Mr. Gilad Shainer, Chairman, HPC AI Advisory Council. Mr. Shainer will be sharing on HPC AIAC, Cloud Native Supercomputing for the masses. Mr. Shainer, over to you.
Thank you very much. Happy to take part and happy to present as well. Sorry that I could not be physically in Singapore. I hope that I will be able to do that next year and be back to Singapore. It's a great city to visit. So I'm Gilad Shainer, and I represent the HPC AI Advisory Council. I'd like to present to you, discuss with you today, essentially bringing supercomputing to the masses. First, a little bit about the council itself. The council was established in 2008 with the main mission to bridge the gap between HPC and today also AI technologies and their usage, to enable a better understanding on new technologies, directions, research areas around the technology itself that enables us running more complicated applications and algorithms on top of that. The council itself includes more than 430 members today. Commercial companies, universities around the world, research centers, government labs, and others. And it's running multiple activities as part of the mission. One of the activities is working with the industry on one side, and then working with the developer community on the other side, to expose different kind of technologies, capabilities, all the way from hardware components to software frameworks and so forth. We operate a small cluster center, compute center, that was created and is being managed by a donation of our members. And on that cluster center, we are conducting a lot of application research, profiling, and explorations to understand how to optimize their performance, optimize the usage of them, how to tune, what's the effect of different kind of hardware and software components. We also provide free access to our members to the center, so they can do their own testing, their own benchmarking, their own development. Here is a subset of applications that we have explored over the time, with full profiling and looking on the effect of the different hardware and software components on their application performance and scalability. Everything we do obviously is published on the council website, so you can find the results and you can find our findings on the council website. We're also managing, by the way, 3 student cluster competitions every year, and that's enable us to actually get in touch with the young generation, and doing those competitions essentially help to enable the next generation of HPC researchers and professionals. So we see that as an important mission of the council as well. So I wanted to talk with you about bringing supercomputing to the masses. Essentially, if we look on HPC in the recent years, and obviously AI is another area of HPC. It's using it needs the same capabilities. We're seeing how AI is being fused into HPC or scientific computing, for example. And we see that HPC is going to more and more places. Growing amount of applications, growing amount of users. And in the future, every company will need to have a supercomputer, access to supercomputer, which means it's in order to do that, supercomputing needs to become a service. Same as electricity is a service. So if we buy an electric machine, we don't need to build our own power plant. Computing has become a service. If we need computing resources, we essentially can go to the cloud. And again, computing resources there. And now we need actually to bring supercomputing as a service. We need to enable access to supercomputing capabilities to more people on demand. And for doing that, we actually need to take supercomputing to the next level. And what we need to do is to be able to combine cloud services on one side with supercomputing or bare metal supercomputing infrastructures on the other side. So far, it wasn't really possible because enabling cloud services, which will enable us to bring supercomputing as a service, enabling cloud services on supercomputers means that we're going to reduce from the performance capacity of a supercomputer. Doing isolations, protection, security between users, performance isolation, and so forth, that brings a big toll. The infrastructure workloads that enables those services is a workload that grows in complexity very, very quickly. And therefore, bringing the infrastructure workload to enable supercomputing as a service, essentially will reduce from a supercomputing performance. Therefore, we need to build the elements, we need to build the components, we need to build the frameworks, we need to build the full stack that will enable us to combine cloud services on one side with bare metal performance on the other side. And this is what we call cloud native supercomputing. Bare metal, secure, isolated supercomputing infrastructure. So looking on the traditional way of the traditional HPC data center, essentially we have the different components, obviously, the compute elements, storage elements, and the network that its main responsibility was to move data from one side to another side. Move data between the servers, move data between the storage, but that's it. Now, this traditional setup is not enabling us to actually bring new services without reducing from the performance of the system. And the reason is that everything that we bring here, any workload, any new workload that we'll bring into the data center here, we need to run on the same compute devices that runs the applications. And looking on cloud infrastructure today that enable computing as a service, we could estimate that around 25% of their compute resources in the platform that they build is wasted on the infrastructure, is wasted on security, is wasted on isolation, is wasting on on enabling that multi-tenancy in their platform. And that's something that we don't want to bring into supercomputing, as we want to maintain bare metal performance. And as such, we actually need to enable or to build new devices. We need to build new devices that will enable us to bring new workloads without running them or running those new workloads on the same compute devices that runs the applications in our supercomputer. And the best place to do that essentially is to reuse the network that we have. But we need to take the network into the next level, which means that instead of having a network that just moves data from one side to another side, if we enable computing resources on the network, if we bring computing capabilities on the network, we can actually create a new computing domain, which is actually a secured computing domain, because this computing domain does not host the users, and that new computing domain can be the one that hosts the infrastructure services. Of course, we need to bring other elements into the network if we want to make the network the ones that transform our supercomputer into cloud-native supercomputing or cloud-native supercomputer, and that will include enabling performance isolation, not just user isolation or job isolations. We also need to look into performance isolation. We need to enable accelerations for multi-tenants. So previous accelerations could be more suitable for single large users, kind of a typical usage, but we need to bring those accelerations, network accelerations, into multi-tenancy and so forth. But if we bring in those elements together, and we bring in the computer into the network, we can actually create a new domain, a new hybrid domain, and that new domain can actually bring or enable the resources or the infrastructure workloads that we need in order to bring supercomputing as a service. So let's look on a couple of areas that are being developed that actually enable us to move into this direction of cloud-native supercomputing. First, let's look on in-network computing. In-network computing started several years ago with the motivations to start or enabling accelerations of different kind of communication-related activities. For example, data reductions, such as MPI reduce, all reduce, barrier, broadcast, and so forth. Those reduction operations running on the host, on the CPU, have become a performance bottleneck. And continuing running data reductions on the host, on the endpoint, on the CPU, would means that we need to send growing amount of data within a data center as part of doing data reductions for systems that are growing in size. And the time that it takes to run such reduction operations depends on the size of the system. The bigger the system, the more time it's going to take. So that become a performance bottleneck. And a few years ago, technology was created to actually move data reductions into the network devices. And doing data reductions on the switch network, for example, enable us to reduce data motion by 2x. It enables us to reduce the bandwidth in the network for doing data reductions by 2x, and enable us to actually get flat latencies for data reduction operations. You can see the illustration here. This is an example of comparing data reductions done on CPUs versus on the network, on in-network computing. On the left side, I took here the recursive doubling algorithm. Obviously, you can take some other algorithms that might be more effective or less effective, but essentially, you can see the complexity of doing data reduction among multiple processes. On the right side, if we're doing data reductions on a network, the only thing that you need to do from an endpoint perspective is send data to the network. The network do the data reduction and actually send the response back. Now, as part of moving towards cloud-native supercomputing or supercomputing as a service, the accelerations on the network, such as in-network computing or the data reductions, needs to support multi-tenancy. So the network that previously supported, let's say, 1 or 2 large message reduction trees concurrently, and that would be great for large-scale users, will now need to transform itself to actually support multi-tenancy. And we've seen that coming on the latest generation of InfiniBand network, where every InfiniBand switch, every new InfiniBand switch now actually supports 64 concurrent large message reduction trees, which is essentially virtually unlimited if you take into account the number of ports that every switch has. or supports. And by doing that change, by supporting the growing amount of users of virtually unlimited concurrent reduction trees, now you can actually bring the in-network computing data reductions into multi-tenant. So this is one important change that actually enables us to go to the new supercomputing architecture. The other thing that needs to be addressed is performance isolation. And here you can see an experiment that actually demonstrates the problem. We took one scientific application as example. In this case, it was lamps and molecular dynamic code, and we run it in 3 different configurations. The one on the left, represents the results of running lamps on a dedicated supercomputer. So lamps was the single application, the only application that was run on that system, and we run the same code over and over again. And every time we recorded the result and actually created an histogram, it showcased the results. And you can see here that the histogram is very, very narrow, which means that every time we actually got the same result as expected. In the middle graph, in the middle of the page, you can see the results of running lamps, but now not as a single application, but in the presence of other workloads. Massive storage workloads, massive all-to-all workloads, and so forth. And now the results are completely different. Here we can see that applications running on our infrastructure actually impact our own application. And you can see the same things, by the way, looking on the other workloads as well. So the different workloads impact performance of other workloads, and now we don't get the same performance over and over again. You can see the spread of histograms. So every time we actually get a different performance, and it could be even 2x or 3x worse. So this is something that needs to be addressed, essentially to bring performance isolation. And new elements that have been brought to a new generation of networks, such as InfiniBand, that what we explored, actually enabled the network to control the usage of its resources, to make sure that one workload does not impact the performance of another workload. And you can see the results on the right side. The dashed line represents the performance that you see on the left slide, meaning the dashed line represents the performance of running lamps as a single application. The green line represents the performance of lamps running in the multi-tenant environment. And you can see here that actually the results are becoming the same. And that brings performance isolation, or actually bring predictive performance. We did some testing on Azure, on a public cloud here. And did some preview testing of the new technology capabilities. And what we did here is actually we took 3 different codes. We took lamps, we took a CFD code, and we took VASP, a quantum mechanical code. And we did the same experiment again. So on the left side, you can see the results of running data-specific application as the only application on a system. It was 400 nodes on the cloud. So running lamps as the only application got us nice histograms of results. The same with Incompact 3D and the same with VASP. In the middle, you can see the results of running the same application, but now in the presence of other workloads. Now it wasn't just the only application running on that system, but it was running in the presence of other users and other workloads, and you can see the spread of histogram. So we can have half of the performance from the get-go, and it could be even 5x worse in the heavy usage of other workloads in the same cloud infrastructure. And then on the right side, you can see the results when we actually enable the performance isolation. The dashed line, again, represents the original performance results of running the application as a single application on the cloud instance. And the green one represents the results of running the application in the presence of other workloads. And we're getting very close. We're getting very close. So performance isolation is another key element. It's doing the accelerations for multi-tenancy, and then performance isolation is another key element in order to bring supercomputing as a service. Now, there is other things that needs to be developed. And I mentioned that in order to bring isolations and security, or the job isolations and the multi-tenant security, we need to bring new workload into the supercomputing infrastructure, and that new workload cannot run on the same domain that runs the other workloads. It cannot run on the x86, for example, the host CPUs. Therefore, beyond in-network computing for multi-tenancy and beyond performance isolation, we also need to build a new or enable a new computing infrastructure. And that new computing infrastructure is enabled by the new devices that are referred to as the data processing units, or DPUs. DPUs are devices that actually replaces the NICs. Replaces the NICs in every server. They have the full NIC functionality. That's the network interface. Those devices completely include the full NIC functionality, but beyond of the NIC functionality, which enable them to replace the NIC, the network interface card, they also include multiple programmable cores. It could be ARM cores, for example, but multiple programmable cores, specific hardware engines for the infrastructure workload. Because if this device needs to run the infrastructure workloads, it needs to be designed to do that. It needs to be more effective than running their workloads on an x86. Else we would use an x86 for that. They need to be much more effective than that. And they are more effective than that because they have specific hardware engine for storage management. They have specific hardware engines for security, for isolations and so forth. And those are the specific hardware engines that enables those devices to be a great infrastructure processors. So actually it's a full data center on a chip. So we replace the NIC with a data center on a chip device, and that data center on a chip device becomes a new computing domain specifically for the infrastructure workloads. And that means that we can take the traditional architecture of a supercomputer, where everything runs on a host, and migrate those elements into the new computing domain that we just enable on our infrastructure. And migrating the management, the isolations element, the monitoring, the telemetry, the file system management, cluster file system, network file system, move that management into the DPU. And bringing the isolation, bringing the security, the DPU is a device that provisions now the server, controls the server, load operating systems, clean residual information between different tenants, and so forth. Now, the DPU will bring us capability to do other things, which is a great thing. But first and foremost is to enable supercomputing services. And with utilizing the data processing units, we actually transform the supercomputer to become more of a zero trust architecture. We secured everything after the DPU, which means the tenants, the users, stays within the server. They're isolated among themselves, and then everything outside is controlled by the DPU. So actually, you virtualize the storage access. The DPU is the one that controls storage access. You can determine if you have access to a storage area or don't have access to a storage area. It represents storage to the tenants running on top. Everything outside is secured. Everything outside is secured by the DPU. And that enables to control tens of thousands of concurrent isolated users on a single data center. So that's the key element in order to bring the security that we need in order to support more users in a secured way on a supercomputer. Now the DPUs bring us even more elements there, because the DPU is a new computing domain. Computing domain running the infrastructure, but we can utilize that computing domain to do other things. This new computing domain sits very close to the network, sits on the network. It's very close to the data. And therefore, we can actually utilize that new computing domain in order to migrate operations related to data communications, move them from being executed or done on the host and actually do that on the new computing domain, do that on the DPU. So we can essentially enable computational storage now, in a much more effective way, utilizing the DPU. We can use the DPU in order to migrate communication frameworks, migrate non-blocking operations, migrate more of MPI work, essentially. So communication algorithms can now be done on a new computing domain. And that new computing domain, enabled with RDMA technology, can actually do data manipulations on the host memories, either locally or remote, completely bypassing the CPU. So that means that we can migrate work from host processes to workers processes that runs on a DPU. And with that, be able to, for example, move MPI to be executed or managed by the DPU. One example is looking on non-blocking collector operations, where the host processes essentially send metadata information to the processes running on the DPUs. The processes running on the DPUs will utilizing RDMA in order to do data manipulations where needed, and then actually report back when the completion is done. By moving MPI or non-blocking operations of MPI to run on the DPUs, we can gain great overlapping between compute and communication. And having overlapping between compute and communication essentially enable us to hide latencies for applications. And if we look on different kind of applications, and I took a subset of 4, just an example, VASP, GFS, GROMACS, and GSI. And we did profiling of those applications, and you can see that VASP, for example, more than 30% of the time of VASP is spent in MPI. 20% of GROMACS application spends in MPI. So if we enable overlapping and actually running that MPI portion on a different domain, on the new computing domain, on the computing domain that we brought to do the infrastructure, but now we can reuse that to run MPI, we can reduce that time and actually have that done in parallel with the right modifications to the applications below in order to be able to take advantage of non-blocking operations. So there is a great promise here, not just from the infrastructure, not just bringing supercomputing as a service, but also to use the DPUs in order to accelerate application work. There is several consortium that is putting resources right now in order to create the infrastructures to utilize the DPUs or the computing on the network for such operations. The UCF consortium, for example, which managing the UCX framework development and UCC framework development, is managing OpenSnappy, which enable also access to in-network computing or DPUs, for example, in order to migrate MPI operations and migrate OpenSHMEM operations into the network to be able to achieve that overlapping. So great things are coming, and we're very happy to take part of development being done in across multiple entities, research centers, and in commercial companies. The council itself is going to host several conferences this year. There are 2 that is coming, Switzerland time zone and Stanford in the US time zone. Both of them is going to be virtual, which will report progress in multiple topics, also the topic that I presented here. There will be other conferences later the year in the UK, Australia, and so forth that might go back to be physical conferences. So with that, I'd like to thank you for listening. By the way, more information about the council you can find on the council website, and if you'd like to join as members, and memberships is free, more than welcome to send us an email and we'll take care of that. Thank you very much.